Okay, so today is just the midterm review. So I'm just going to go over some basic structure here, and then happy to take questions or walk through some slides that may help generate questions. So just sort of looking forward here. The next reading is not till lecture E4, so we're going to start unit E after the midterm. So the midterm is going to be all next week, and then I think fall break is like right after that. So you don't start lecture E1 for a while. And so the next reading you have to worry about is E4. So if I'm doing my fall break math right, then it's like, E1 is a Thursday, and then there's a week of E2 and E3. And so then you don't have to get to chapter 6 until like the week after that. So it's quite a while away. But I might recommend skimming through, say, chapter 5. I think it might be useful when studying for the midterm. There's some good comments in there that are kind of related to some of the things we've talked about. Otherwise, Muddy's Point due on Sunday, that VinSim assignment, D3, the kind of VinSim toilet model, is also due on Sunday. After the midterm, because depending on how you guys decide to use the midterm, I might not see you next week. There will still be a Muddiest Point that week, and you can focus on sort of the midterm. So what do you think were the clearest parts of the midterm, the muddiest parts, any sort of new insights? That would be, sort of what to do turn in Sunday after the midterm. And then in the midterm, we'll remind you of this towards the end of it too, but final project groups. So basically you're going to have your midterm, and then the Sunday after lecture E1, so it's sort of like a week after the midterm's completed, I'll expect you to have formed your final project groups. So definitely start working on that. You can think about that, during stage 2, as you start working with people, noticing who you have good chemistry with. You can post things to that Google Sheet that's online. There's already a couple people who have posted there who are looking for team members. So take a look at that Google Sheet that I've linked online to try to make those pairs, shooting for 3 or 4 person groups. And then the midterm. And so we're going to talk about this today, but basically at the top of every module, there are learning outcomes, which are basically a study guide. So what do I think you should know at the end of every module? That's at the top of each module. I've listed those. And within the midterm module, there are some practice problems and solutions. You'll have to take the Canvas, the lockdown browser compliance test for the midterm. Once you take that, that'll unlock the midterm module. And inside there, you'll see, exams from previous semesters, some other practice problems, and other resources as well. So definitely recommend you take a look at that. And then Tuesday, we'll have stage 1. So that's an individual exam. It says Thursday, but yes, these are swapped. So remember, the last time I taught this was spring semester, and the schedule for fall semester is off. And so unfortunately, I can't just grep through all my PowerPoint slides, and so I missed this. This is supposed to be Tuesday, and this is supposed to be Thursday. And when I teach it in the spring, they're not in the same week. So Tuesday, and I'll go and change this, that's when we have stage 1. That's the individual exam. I've opened up the availability window for stage 1 to be all of Monday, all of Tuesday, all of Wednesday. So by that, I mean from midnight Monday to 11:59 Wednesday. And so 72 hours starting Monday that you have to start the exam. The exam is a Canvas-based exam. It requires Respondus lockdown browser. If you want to come here Tuesday and take it in class using either these computers or your own laptops, that's fine with me. You don't have to. I provide 90 minutes. It's designed for 75 minutes. And when I say designed for 75 minutes, what I mean is I expect most students to probably finish with it after about 40 minutes. Some will take longer, some will take shorter. So I think all of you will be able to finish it within 75 minutes normally. I provide the extra 15 just for any technical issues that have to do with Canvas. And so if you want to come here, there's nobody that comes after the class, and I'm willing to hang out for 15 more minutes so you have your full 90 minutes. If you want to take it here, you do not have to come here though. Take it wherever you'd like. You can start it Monday, Tuesday, or Wednesday. It just needs to be done by Wednesday at 11:59. So that's the individual exam. It has to be done. Right, well, that's what I mean by done. So you have to either submit it. If you go over that 11:59, Canvas submits for you automatically. So that's what I mean. You have to be done. by 11:59, or else Canvas will truncate your exam at 11:59. Then stage 2, Thursday at midnight, automatically will pop up, and I've given you Thursday, Friday, and Saturday, that whole availability period. That is not a timed exam. It's a group exam. You can work with anybody in the class in this current semester. You can use your book, you can use your notes, you can open up Vinsim if you want, or Insight Maker. Insight Maker is the only sort of internet resource that I'll sort of allow you to use. But otherwise, so yeah, you can work together. It's exactly the same exam. You will not know your scores for stage 1. You will not have the solution set for stage 1. But at the end of stage 1, I remind you before you hit submit that I also allow you, not only do you get one double-sided sheet of hand-produced notes, but I also let you have some blank sheets, and you'll show the camera your blank sheets. So at the end of the exam, I remind you, it's not a bad idea to go through and write down what answers you put down and whichever problems that you thought were most, that you struggled the most with. And then that way, when you go into stage 2, you'll know that those are the ones that you should brush up on, and you'll be able to make sure that you're sort of consistent with the answers that you did in stage 1 for the ones that you maybe, if you just want to know what you did there, so you don't have to rethink all of those problems again. So stage 2, again, is supposed to be, I say it's a group exam. You don't have to take it as a group. You can work alone, just have it open notes or whatever. And then I forget how much the exam totally is worth. It probably says on one of the next slides here, but let's say it's worth 20% of your total grade. What we're going to do is we're going to take your score for stage 1, multiply it by 80%. We're going to take your score for stage 2, multiply it by 20%, and then add those two weighted scores together. That will be your score for the midterm, and that goes into calculating your final score for the course. So yeah, question? Yeah, that's a great. So there, like all of, you don't need to memorize all of the archetypes. I have, I think on like the second page of the exam, maybe the second and third page, I have a table of archetypes that's taken from some of those resources that's just reproduced for you. So those are available. They're going to be like the little kind of cartoon archetypes and like maybe some very brief descriptions. They're not going to go into great detail. So you have to sort of remember how to parse them, but it should help jog your memory that, oh yeah, there are two different types of archetypes we learned with the balancing loops. And this is the two balancing loops together. And these are the differences between them and so on. So if I were to ask you in the exam, like, here's a scenario, which archetype do you think best fits this one? You'll be able to scan through that. So yeah, you don't have to write down all the archetypes on your one sheet, your one double-sided sheet. Any other questions online as well? Taking a look at the chat. Okay. All right, so yeah, so today just sort of designed to be a midterm review. So basically, just stop me as you have questions. I have got, these are, all I've sort of done here is for the 4 units that we've covered, I've got kind of a cover slide that has the name of the unit and the learning outcomes. If you go to that module on Canvas, you will find these learning outcomes. I think I might even call them now study guide. And so these are the things that I think you should know coming out of Unit A. And so when I build the exam, these are kind of the things that I'm trying to kind of test you on. And so I'm going to have like a cover slide, and then I'm going to have a couple of slides where I've basically pulled out slides that I think are kind of the greatest hits from that unit, where if you're prioritizing what you're studying, these are the things I would put the most sort of time on. I'm not saying these are the only things. I mean, anything we've talked about in lecture is sort of fair game, but these are the things I would sort of prioritize if you're kind of like, trying to make the best use of what little time you have left. So before I go on, just to sort of hit the things that I, go back to these fundamentals, are there any burning questions that people want to have answered? Make sure we get answered today that you came to class with. Anything? Are the slides on Canvas? Yes. If you go to that's a question from online. If you go to the midterm module, it's like unit D2 or something, I don't know. But if you go to the midterm module, you'll find these slides. You may have to take that Canvas lockdown browser compliance test. Let's just make sure that you can run lockdown in order to get access to the module. But once you complete that, which is like you open it up in a lockdown browser, you check on a checkbox, you hit submit, and you'll be done. Then you can get access to these slides. Any other questions before we plow on through? All right, so going back to the basics here, I would say this quote up here, models answer what if questions, will be something that you should definitely have down. So models are defined by how they're used, not what they're made out of. And so, models can be made out of people, like Soylent Green. They can be made out of math, like this sort of Bohr model in Atom. They can be animals. They can be computational. All of these things, they can be graphs. All of these things are models. And it's not their substance that defines them as models, but it's the fact that they are being used to answer what if questions. And so that's kind of this important distinction. You're trying to understand what these models are. And there are different types of models that we can focus on. And we can say, why would you use one model over another? And we said, that their mental models are great because that's where we get a lot of our information to reason about the world from our experiences, from the experiences of others that has been communicated to us. The downside is not so great at dynamics. So that's why we've got quantitative models, including mathematical models and computational models. They're much better at handling this complexity and dynamic change, but I hope you've seen now that we're starting to look at these models. They're extremely simplistic. So they only include the very little bit of information from the system that you have chosen to put in them. And so if you leave out something important, the model will not necessarily be very informative. So of quantitative models, we've got math models. So you could write out some equations and you could solve those equations. It's great because those solutions are illustrative of maybe some interesting features, but they can be difficult to solve. They can be hard to understand. And they often, in order to actually do the solution, require you to make some assumptions about what you care about, which is why we have simulation models. They're fast, but they're approximate. They actually do give you dynamical behavior, extremely easy to change. And you can add in a lot of complex concerns into them and demonstrate how those concerns come together in novel ways. Downside is they don't have the nice equation outputs. And a lot of times you're going to depend upon decisions made by whoever built VinSim or InsightMaker or whatever. And so that's a big reason why we had to learn about spreadsheets so we could understand how this whole time step thing was all about and Euler's method and all of that, so that when we go into the sim model and it just says what time step and what integration method you want, you at least sort of know like, oh, I know what you're doing behind the scenes there. Because otherwise you're just taken for granted that the programmers have done the right thing. So that's kind of, they require us to know a little bit more, or they allow us to sort of give a lot of responsibility to programmers, but the trade-off is they're really flexible and super easy to use. So that's sim. So, so any question about those different types of models, mental models, quantitative models, analytical versus simulation? I don't know what that means. Because what it means to be provable. Well, but truth is only defined in terms of axioms, and so the math. That's right. I mean, math doesn't describe anything in the real world. It's just a tool we use to make sense of the real world. But we have no reason to believe that. That's right. Right. Any other questions about these? Just the general different the separation between the types of models. All right. This is stuff from like the very beginning of stuff. This modeling spectrum is another thing I could ask you about. This idea of very detailed analog models, all the way to metaphorical models that are extremely simplistic. Our models in this class are hopefully somewhere in the middle, probably biased more towards here. But the idea here is that as you give up detail, you gain generality, which helps you make broader statements. But when you actually need to really fine tune your understanding of a system, then it requires trickling in detail as you go. So there's a benefit to all of these models. No one model is better than another. So ideally, for your particular question, you will choose a model that is the least costly and provides you the maximum insight. So that for you, that balance could be here, it could be here, it could be here. For most people, it starts here. And once you get an insight, you trickle in more detail and you get farther and closer to this way. So you might talk about all diseases. You talk about then diseases that have particular properties. You talk about a specific disease. And so then you finally get to a treatment plan. So that's kind of the standard sort of method is all of these models are important, but we often start here and then work our way this way. All right, so any questions about that? It's just sort of our basic Unit A intro to modeling stuff. All right, any other questions that come up too? If like, as I'm talking, like, oh shoot, I have a question about spreadsheets or whatever. You don't have to wait for it. Just let me know. This is your time. So causal loop diagrams. So this Unit B, we start to actually diagram out the things that are in our head. And this was a tool for us to try to write those things out so that we can understand what variables are important, what to leave out, what to leave in. And do things like identify feedback loops. That's really important here. And that requires us to label our causal loop diagrams. And then I'm not going to ask you specific questions about VinSim. Like I'm not going to say, where do you find the time step in VinSim? But you should, if I show you a diagram drawn in VinSim, you should be able to know that's a flow, that's a link, and so on. I mean, I haven't got the flows yet. We're just talking about CLDs. So be able to interpret outputs from VinSim or Insight Maker or Moorcroft's Stella, or I think, but I'm not going to ask you technical, practical questions about VinSim, not at least here. Maybe on the final exam, but not at the midterm level. We're sort of just kind of starting there. So CLDs are kind of in between the very, very high level view of the system and a more detailed view of the dynamics. You can go both ways. So if you have sort of a high level view of the system, the CLD helps you get close to the model. Or if I give you a model, you can then diagram out the CLDs. And so, so this is kind of blending this unit and Unit D, but you can imagine that I might give you a stock and flow model and ask you, where the feedback loops are. Or I'll ask you, did I annotate this stock and flow model with the right feedback loops? And that'll require you to draw a causal loop diagram from the stock and flow. So CLDs can be used in both ways. So, and then make sure that we know how to, label these things. So if I give you a description of C and a description of X, that description could be a verbal description. Like I could say, the more, the more instructors there are, maybe the more learning that goes on. And so if this is amount of learning and this is amount of instructors, then we know there's a positive link there. But I could also give you a formula. Like I could say that X is equal to 1 divided by C. Well, if it's 1 divided by C, then if I make C bigger, X will get smaller, and that would be a negative. So if I give you descriptions of variables, can you then place, the labels on these links? And you have to kind of think of it relative to sort of a no change baseline. So if we're already thinking of a dynamical situation, like if X is already growing, then I have to ask, would it grow more or less if I change C? So these aren't always interpreted statically. I have to sort of think like, will the growth be more or less than the growth if I didn't change C? That's what I mean by a no change baseline. All right, so any questions about labeling links? I know back in this unit, this came up, I think, in some of the muddiest points. Like people were saying, I need practice labeling links, and hopefully that's gotten a little easier. Definitely something that we'll touch on. No, I would have to tell you what C and X is. Yep, like I'd have to give you a formula. X is equal to C times A. If I said X is equal to C times A, then this would be a plus. Because if I increase C, it would increase X. Also, if I increase A, it would increase X. Okay. Loops, finding those as well. So once you've labeled these things, then you have to know to count the number to be able to find loops. So you can start at a variable and follow it all the way around to the variable again. That's important to find loops. And then once you've got that, you need to count the number of negatives. The odd number of negatives, a negative feedback loop, even number of negatives, positive feedback loop. So being able to recognize those. All of the terms here, snowball effect, positive feedback, virtuous cycle, vicious cycle, these are all synonyms for positive feedback. Likewise, negative, balancing, counteracting, all synonyms for negative feedback. And I should, and this, now that I'm thinking of synonyms, when I go back to labeling links, this plus and minus, remember, these also could be labeled S for same or O for opposite. So know that plus and S are the same and minus and O are the same. So if I grab a causal loop diagram from another textbook where they use S's and O's, I'm expecting you to know that the S's are positive and the O's are negative. Okay. So any questions about the loops, either their labeling or the naming? Questions online? The plus is S. Positive is same, negative is opposite. It's like thinking about a negative correlation. If something's negatively correlated with something else, it moves in the opposite direction. So then, be able to do things like this. So we did exactly this exercise before, label the loops. And remember, there were 3 loops here. There was a loop that went from A3 all the way back around to A3. There was a loop from B3 all around to B3. And then there was a long loop all the way around the outside. And so I promise that if I give you these things, they're not going to be, they're going to be somewhere in between super tricky and super easy. I'm not going to hide loops. I'm not going to try to move links to make them really close together to make them hard to see. And if I ask you here, I might even tell you, I might even say find the 3 loops, so that you'll do that. So, but still, if I ask you to find the loops, just be careful that you're trying to account for all of the loops. But I'm trying to try not to give you any trick questions but they can't be super, super easy because I need to also sort of assess that you're knowing to look for all the loops. Also find errors in loops. And so here, this is a negative feedback loop because it's got 1 negative. Here, this is not a feedback loop because all roads point to D. D does not come back on itself. So this should not be labeled as a feedback loop. So any questions about labeling loops? Okay, questions online? All right. The correlation and causation issues, so avoiding the sort of post hoc ergo propter hoc and cum hoc ergo propter hoc fallacies. So in this case, these 2 things are correlated together. They are positively correlated. As ice cream sales go up, so does sunburn rate, but there is no causal connection between them. There is a common cause. As average temperature goes up, so do ice cream sales and sunburn rate. So this is the correct CLD. This is not. So this is one of our rules. Causal loop diagrams are not correlational diagrams. They have to make an assertion about a causal theory. And also, there's rules for how we pick the variable names that hopefully are maybe making more sense as we're trying to build stock and flow diagrams, is that we need to make sure that they're noun phrases. So putting verbs in here like costs rise and price rises, we want the action to be in the link, not in the name. So we'd rather just to be cost and price, and then we can say as costs go up, so does price. And we want to make sure they have a clear sense of direction. So just saying feedback and attitude, those aren't clear what's the direction, but praise is clearly measurable. There's no argument of which direction's which, and morale also has a direction. And the normal sense of direction, and this is less important, but this is a sort of a standard convention, or this is, I don't want to say standard convention, this is a convention that we try to make the normal sense of direction to be positive. So we would say that, instead of saying losses, we'd say, well, it's better to sort of say profits. And so that, again, is not super important, but when we're starting out, if you don't abide by this rule, it's easy to trick yourself into putting the wrong link in. So you have to kind of, it's weird to think as costs go up, I increase my losses. It's a little bit easier. Usually it's cognitively more ergonomic to say, as costs go up, my profits decrease. So that's kind of what we're saying here. If I ask you sort of tests about this, I'm going to probably focus more on these categories up here and this, these, and this here. I just throw that in here because this was on the slide, but because this gets a little subjective, I'll probably hold off on doing a whole lot here, but you should still keep that in mind. All right, so well, I guess I put that, this is sort of the same sort of thing. Noun phrases, avoid verbs. Measurability, or I like to say sortability, those are kind of the things there. So any questions about these rules for drawing CLDs? Again, these are all slides you've seen before, or questions about anything else that just have come up. Again, I want to make sure it's the best use of your time. Okay. So give you a process, ask you to diagram it. So you look at the process, you have to choose the variables, you have to choose all of the labels here. So if I look at a simple process like this, I'm filling a bucket, then I can say, well, the water level is probably one variable, the flow of water is another variable. As water level increases, the flow of water will decrease due to the control. As the flow of water increases, water level will also increase. So this end will be positive and this end will be negative. So we've kind of already done that one before, so I won't annotate it here, but any questions about this? Does this feel like something you could do? If I gave you a description of a system like this, could you sort of find the negative feedback or the positive feedback and diagram it out? No, I have a variety of different, so I have multiple choices, I have fill in the blank, I have matching, I have calculation questions where I can give random numbers and allow for the random things in response. Aspect of that process. So if you have to calculate a bunch of numbers, I mean, in this class wouldn't be calculating that much. I might ask you for the sum of those numbers. And so if there's a bunch of exponents in an equation or something like that, you could, I might ask you to add up all those exponents, and then that would be a check on your answer. So kind of like a checksum in a bit string. But so there's, you know, I write these things as if they were written, and then I try to come up with clever, or hopefully clever ways to then chop them up into ways that Canvas can auto grade them. But it is a Canvas administered exam after stage 2 is released. I will then, once I make sure all the stage 2s are in, I'll release the solution set and your scores will be about immediately available. So it is an auto graded exam. So expected to kind of be Canvas-y or Scantron-y. I like to ask a lot of sort of like select all type questions too. So it won't just like be like multiple choice, choose one. You might have to choose all, or maybe the right answer will be to choose none. So, and all of the questions will be the same point value. So even though some questions might take you more time, overall, like, you know, in the real world, you're not rewarded for the amount of effort, you're rewarded for an outcome, even if that outcome didn't take you, you know, hardly any time. So concepts are just as important as calculations. So, so if I do think it's important to capture steps in a calculation, I'll break that up into 3 questions so that your success on one doesn't cause you, your success on a downstream one doesn't require success on an upstream one. So you'll kind of get to reset and start in the middle of the problem for the next one. So if you want examples of that, again, there are sample midterms from previous semesters. I think I've even in this class have at least one Canvas-based sample so that you can actually take as many times as you'd like. So you can see how I've done this in the past. Yeah. Yeah. Great question. So, so it could be. And I do see the question online. I'll get to that in just a second. So so the question is, let's bring up the annotations here. Did that show up? Yep. All right. So, could I include the hand? I probably could if I wanted a very detailed model of this. But for this system here, what I probably would just do is sort of say water level. And down here, flow. And then I would model the action of the hand kind of within the link. And so I would say that, well, I mean, this link is just by physics. If the flow goes up, the water goes up. But the hand, I think, would show up in this link. So, so the idea here is if the water level goes up, the flow goes down. And so this minus here reflects the policy, the control policy that is being implemented by the person who's monitoring this and using their hand. So we could imagine a much more detailed CLD where we could actually put like angle of hand here or something like that. And then as long as we agreed on the coordinate frame, we could say, well, as the water level goes up, the angle of the hand moves in this direction, which causes the flow to do this thing. But that's kind of getting probably more detailed than we need to. It doesn't, this is, so the salient features here are just kind of, wiping out this sort of nuisance variable of what the hand is doing. Does that make sense? Okay. Any other questions about this one? I did see the question online, which I'll get to in just a second. All right, so there's a question online. Are we going to be asked to do any Excel work? You should know the fundamentals of how to do numerical integration in Excel. The biggest things are like, what the heck is a time step? And generally, what does it mean to step through these sort of systems? I'm not going to ask you for what is the correspondence between a differential equation and an Excel spreadsheet. But the biggest thing that I was trying to get you to do by doing all those Excel examples was to sort of feel kind of in your bones what stepping through a dynamical system is doing. And the time step is like the biggest thing. So I'm not going to, again, there's not going to be a lot of like practical, like lab practical type questions on the exam, but I might ask you, like, here are 4 graphs of systems, the same system with different time steps. Which do you think is the most effective time step for this? And you'd have to know, I think I might even have that example coming up here. You'd have to know it's sort of the time step that is the largest, that any time steps smaller than it have produced basically the same graph. And so you want to kind of the graphs to converge and not go to too many time steps smaller than that, because that's going to give a lot more computational effort. So those are the types of things that I want you to know. Whether I'm not going to ask you to like, all right, here's a spreadsheet, what formula to put in. I won't ask you spreadsheet formula questions. But I guess I could do something creative, I guess, where I could show you spreadsheets where the formulas are filled in, and I might ask you to identify where are the flows in this, where are the time steps, where are the stocks, those sorts of things. Yeah. Exactly. That's exactly what I'm talking about. So for those online, so they're saying, when I say time step, I mean DT, and the general rule that if you make it larger, the larger you make DT, the more inaccurate your simulation is. The smaller you make more DT, the longer the computer will take to generate the plots. All right, any other questions online or in class? Okay. All right, tab back here. All right, so again, give you, this is an example we did in class. I'll give you, if I gave you something that looks like this isn't the greatest CLD, but the base idea, if I give you an unlabeled CLD and rough descriptions of what these processes are, then can you then translate descriptions of those processes into links and link labels and loop labels? So, yeah, when we covered this back in that lecture. So, so that, when we were, No, I probably would. I mean, all the examples you see on the test are likely going to be fresh examples you haven't seen before, but I'm just sort of going back to the things we've done in class and sort of say, remember that we did that? Try to be able to do that on a fresh example. Similarly, you won't see this example that you did in your homework, but the same sort of thing, being able to label these things. Any questions on CLDs or other things that have come up? Questions online? Okay. So unit C, so halfway done. So this is where we talk about system archetypes and generally systems thinking. So we talked about this event-oriented worldview where you sort of just think about, I'm waiting for problems and then I'm going to solve them as those problems occur. And whereas the systems thinking approach says, I'm going to actually think about how my problems might generate, or how my solutions might generate more problems through interactions which currently are not obvious. So it's kind of the general idea to kind of take the larger picture there. And we talk about how there are certain patterns, like if I've got balancing feedback loops with delays, depending on how big the delay is, I can get different behavioral patterns out, but they all actually come from this same general structure. And so sometimes I get slow rises to my set points. Sometimes I get, ideally I'd want fast rises, but sometimes I can also get these weird things where oscillations occur. So basically, if we learn about these common patterns, and we can also learn about the different behaviors that are likely to come out of them. So if we see these patterns, we can start to anticipate these things ahead of time rather than just waiting for the problems to then, occur. So you imagine I'm implementing the solution here. It'd be great if I anticipated that this oscillation was going to happen rather than just waiting for the oscillation to happen. And if I recognize the pattern, then I recognize that this is a possible outcome that I might have to deal with. So that's the basic idea here, that things like oscillations almost always are caused by some sort of balancing loop in a system plus a delay. We've seen that a lot in supply chain examples. There's a lot going on now in the current events that relate to this. And so just kind of showing this water example is that oscillation with delay. We said S-shaped growth usually happens when a system starts out with a strong reinforcing loop, but as the thing that's growing grows, it ends up causing another process to gain strength that balances that out. And so that's another common thing there. So basically, whenever you have growth, there is almost definitely going to be a balancing loop hidden somewhere in there. So look for it. And then you can combine those things together. And so if you have growth, there will be a balancing loop. And if that balancing loop has a delay, then you might get growth with overshoot. And that can lead to things that look like collapses, because you can get massive ramp ups to be over capacity. And then the feedbacks that help limit you from being too far over capacity come in so slowly that you end up getting into a lot of trouble, and then you end up sort of collapsing. And so this is kind of a motivation that came from the Moorcroft text for the wider variety of system archetype kind of vocabulary that we got in that Unit C chapter from Kim and Lannon. And so I would say these archetypes, the balancing with delay, S-shaped growth, growth with overshoot, those are ones that you generally should know. Those are ones that they are technically ones that are in the kind of Kim and Lannon archetypes, but those are ones that you should sort of just have memorized, and because they're kind of like core, really fundamental nuggets. They are the Lego bricks of other archetypes. But then the actual archetypes that Kim and Lannon go over, the much more complicated one, those are the ones I don't expect you to kind of know off the top of your head. I'll provide those, but you should know how to use them. And you should sort of understand these kind of 4 different ways that Kim and Lannon talked about that you could potentially use those archetypes as lenses, where you can take multiple archetypes and apply them to the same system, and that will sort of give you different perspectives on possible solutions. As structural pattern templates, where you take an ugly giant CLD and turn it into something that's much more manageable. as dynamic theories where you use an archetype to understand why you're seeing a particular behavior over time, and then use that to generate potential interventions to change that behavior over time. And then predicting behavior, which is kind of related to that, where we take a simple, like we never see a reinforcing loop alone. A reinforcing loop alone would grow forever, but we know that's not going to happen. And so what are we can use the fact that we know reinforcing loops never come alone. They always have a balancing loop. So that's going to mean that when we're predicting what's going to happen in the future, we need to also account for the fact that we're probably our growth will eventually saturate, and we need to account for that in our planning. So those are kind of the 4 sort of examples. So any questions about the system archetype stuff? Again, you don't have to memorize all of those 9 or 10 archetypes that Kim and Lannon gave you. I'll give you those, but know how to use them, be able to recognize them. Other questions online? Yeah. Well, yeah, good question. So my goal isn't to trick you. So if I'm saying like, what's the best archetype for this particular example, then in that case, I'm going to argue that one of them will be, predominantly like much better than all of the others. Now, if I was asking like a lenses question, then I could say, like, if you applied this archetype to this problem, what would play the role of this in the archetype? And so that would suggest that the problem could be viewed in multiple different ways. But then I'm now forcing you to say, look at it through this lens, and through this lens, like in the copier example, what is the limited resource or something like that. So, yeah. Any other questions? All right, so the last unit, sort of the much more kind of simulation related unit, Unit D, our most recent unit. So these are the learning outcomes that I'm expecting you to have by the end of the semester. So like when you come out of this class, you'll say, I'll know how to do a simulation. Now, when I say like ability to use a computer spreadsheet to numerically evolve a system, yada, yada, I'm not necessarily going to test you on that on the midterm. So I'm saying this is learning outcomes for the course. And these are the learning outcomes that come out of this unit. For the midterm, I'm not going to ask you, so getting to that question that was asked online, to like, there's at no point am I going to say, all right, go into Excel, do something and upload your results. But you should be able to recognize the steps of the numerical simulation and how things, again, like time step relate to that, so that we can have conversations about a spreadsheet, even if you don't remember all the details to do it yourself. So along those lines, you should be able to think about things like the compound interest process as a stepwise process of a time evolution, where you've got some initial conditions. Every stock has an initial condition. You don't ever update formulas on stocks. You only update initial conditions on stocks. And then once you know whatever the stock variable is, initial condition or otherwise, there are converters that allow you to calculate things that like interest. And so these are the things that you do have formulas on. And so these converters or auxiliary variables or whatever you want to call them, they are going to be functions of the stocks and other converters, which eventually are going to be functions of stocks. And then with those, so that means that stocks can cause converters or auxiliary variables to move. And then those converters can eventually cause those stocks to move. So, so this case here, we've got this iteration here where a stock changes a converter, which then changes the next step of the stock. So, thinking about compound interest as a stepwise process, you understand this, you're like 99 or maybe 75% of the way to understanding any dynamical system broken down as approximated as these stepwise processes. So, so that's something sort of understand, this compound interest idea that, we can calculate in time steps how money changes over time, and how that then becomes an analogy for smoothly changing systems. And so when we think about the average number of bacteria in a petri dish, there are no compounding periods. Like, you can ask at any time, like, now, what is the average number of bacteria I expect to see pi seconds after the start of the experiment? But if I don't actually have the petri dish, if I want to simulate the petri dish, the computer needs time steps, just like the bank needs compounding periods. And so we generate very, very tiny time steps where hopefully the bacteria don't do much. You know, there's a small chance that something will change. And the accumulation of small chances turns into the evolution over time. And so that's the idea here, is that we zoom in on smoothly changing systems so that they look like they don't change much. And then we use those marginal changes to generate an approximation of a smooth curve. And that's what's going on with our bacteria case. So still, a stock is like the number of bacteria. We never update the formula for a stock. We only update the initial conditions. The flows are a special type of variable that is how the stock is changing, the rate of change it over time. And the flow times our dt actually is how what's going on behind the scenes to calculate the interest that actually makes the stock move. And so that's why we want our time interval, our dt, to be super, super small, because we want the generated interest in every time step to be super, super small. Because if your interest is large, then that's sort of missed opportunity for those bacteria or whatever they are to be doing the job of the stock bacteria. So we don't want the stock changing much at all from time step to time step. And this tiny little bit that it does change is what actually allows this thing to approximate a continuous system like the one down here. So with that, that's how we got to this so-called Euler's method, where we've got this sort of spreadsheet here. So I'm not going to have you write a spreadsheet by yourself, but if I showed you something like this, you should be able to find these things. Like, that's the time step. That's an exogenous parameter. It's set from outside. This flow here, this is the flow, which is going to be the stock times some parameters. The flow times the dt, that is sort of what causes the stock to move. So, you know, if I were to show you these sort of three spreadsheets, you know, you'd be able to interpret what the different things are doing if I asked you a specific question about them. And then that relates to then, well, you know, so it's not really efficient to be doing all these numerical simulations in a spreadsheet. So we've got these nice tools that allow us to draw these diagrams, which are equivalent to writing out these mathematical formulas. So you should know, like, I would say this is sort of the most common way to write these formulas. You should know that a flow is the rate of change with respect to time of a stock. So I could give you a simple set of coupled equations that would say, like, dx dt is equal to y plus z, dy dt is equal to x, dz dt is equal to y. And if I gave you those equations, then hopefully you should be able to turn them into stock and flow diagrams. And how would I ask that? Well, I might give you a set of stock and flow diagrams in a multiple choice question that you would choose from. That would be one way that I could do that sort of thing. So be able to translate from this formulation to this formulation and back, and be able to draw causal loop diagrams for either case, for this or for this one here. And so that's kind of an example of this. So here's a formula down here that is represented by this stock and flow diagram up here. And so being able to translate from this thing to this thing, that's a good thing to be able to do. And I think, yeah. So, and then, yeah, remember things like inflows are positive, outflows are negative. So that, you know, shows you that, I'll get to this in a second, but that helps us remember that there's an implicit negative link from outflow back to stock, and there's an implicit positive link from inflow into stock. So any questions about this stuff so far? Questions online? All right. Oh, I'm sorry. You mean these like ones in the middle? Oh yeah, so that in Vinsim, there is a mode, which I haven't shown you guys yet, but we will after the midterm, where you can actually have it generate behavior over time, little thumbnail behavior over time plots in every variable. So so your all the things that I have on the midterm, I won't have these in, but I added them there to sort of show you that because this exogenous variable is the only thing determining birth rate's constant over time, death rate's constant over time, but bacteria is growing exponentially. And because births is a function of bacteria, it's growing exponentially, so is death. So that's what these little lines are. If you were to go into Vinsim and simulate this thing and then click graph on this, you would just see this curve on an axis. All right. Any other questions? Yeah. Yeah, these are the only two feedback loops. And so I could draw those here. So there is a feedback loop, a positive feed, or well, first draw the links. So there is an implicit positive link from births to bacteria. So this loop is itself a positive feedback loop. And then because of that implicit negative feedback loop, and this is the tricky one that it's easy to forget, then there is a negative feedback loop here. And that's what gives this the S-shaped growth archetype. Because we've got the growth loop here and the limiting loop here. Any other questions about that? And this outflows are negative. That is basically saying that there is this implicit negative feedback loop, and inflows are positive is saying there's this implicit positive loop, positive link. Okay, questions online about that? All right. Okay, so this is sort of review then. I mean, I kind of like put a little bit of a bury the lead here a bit, but just kind of remember flows make stocks change over time. Again, just emphasizing this, even though inside Vinsim, you can go into the stocks and it gives you access to the integ formula, the kind of top box, we don't ever touch it. The only thing we touch in stocks, and this I can ask questions about this, are the initial conditions. Initial conditions down here in the instructors 0 equals 0, the initial number of instructors. That's the only thing we touch inside stocks. The only way stocks move is if their flows make them move. So if we want something to influence a stock, we have to connect it to its flow. So there are never, ever, ever incoming arrows coming into stocks. There's only flows going into stocks. There can be arrows coming out of stocks, links coming out of stocks, but no links go into stocks. Only flows go into stocks. And if you want something to affect like the number of instructors, you have to decide what process is that thing influencing? Is it influencing the inflow or the outflow side? And you'd say, okay, let's say, for example, we're trying to compare a school in California versus Arizona State University. And you might say like, well, some school in the UC system is right on the coast. And so the proximity to the ocean is going to maybe increase the recruitment process for the UC school. And maybe the proximity to the hellish desert is going to increase the turnover at the desert school, or something like that. But we would draw the links coming in to the outflow or into the inflow, not into the stock. The only thing we ever update with the stock is the initial condition. All right, so any questions about that? That's like a fundamental, like I could definitely ask about that. Okay, so going along with that, incoming links help enable formulas. So if I said that there's a formula inside a particular variable, you should be able to recognize that in order for this formula to be valid, there has to be a certain structure of the links. So I could give you a formula and I could say, of all of the causal loop diagrams you see below, what's consistent with this formula? And so if there's A is equal to some formula that includes B and C, then this would be the right CLD, because A is taking as inputs B and C. Okay. Other things, I like this notion of sectors. So know the term sector map, know the term sector, this basic idea that this is a kind of a high level way to compartmentalize kind of sections of stock and flow diagrams to make them easier to work with. There is no formal definition of what a sector is. It's just meant to be helpful. But roughly speaking, when you create sectors on top of a stock and flow diagram, then you're going to have more integration, so a lot more links inside the sector than between the sectors. And that allows us to think of the links between the sectors as exogenous variables inside the sector. But then when you plug everything in together, you endogenize all those exogenous variables, and that allows these sectors to influence each other. And that, and the advantage of that is it sort of gives us all the benefits of the simplicity of CLDs while allowing us to have all the detail of stock and flow diagrams. So underneath it all, we have a complex stock and flow diagram, but at the level we present to our stakeholders, we can say, well, rather than you having to see all the ugly stock and flow stuff, just know we've got a general process going on in community that affects the police department and so on. And we don't label these links. We just say there are feedbacks that go from community to police department all the way back to community. And we don't know, is this a positive feedback, whatever. We're just saying there are feedbacks. So it's just a way to present or understand complex stock and flow diagrams that gives us the simplicity of CLDs while allowing us to still have an implementable system. So any questions about this idea of sectors? I think I've got examples of sectors here. So like in this particular example, we just recently talked about this, these are the sectors here. So there's the community sector, the police sector, the street market sector, the drug user sector. And you can see that within every sector, it looks like in the police department, it looks like call for police action is an exogenous variable, like a slider that the designer would slide around and see how it affects the police department. But in reality, it's an output from the community sector. So the SIM is going to know, because these are folders inside the SIM, that these two variables, this is just an alias for this variable over here. So the then SIM or insight maker is going to link all of these up together by their common variable names. So in reality, these four are all connected, but we can present each four independently, and it makes it much easier to present this model. Okay. Questions about any of that? Great. All right, so a few practice problems. So this is, you won't see this one on the exam, but here's but if we can go through this one, then it's just kind of a good example of something I might ask you to do. Now, this is a little more complicated because, you may not know what thrombin is, and how prothrombin activator works and things like that. But if I were to give you something this complex on exam, I would explain that out. I'd say that well, the formation of prothrombin activator is going to increase the amount of thrombin, and you would know that, okay, that means that I put a plus here. So I could go around this thing, all of these, and I probably wouldn't give you something where you have to label this number of links. But if you can label this number of links, then you're probably in pretty good shape. So you label the links and label the loops. So I don't know if I want to necessarily go through as a class exercise and do all of these, but if I sort of start on this, then we can see that there's some interesting feedback loops that are going to come up here. So for example, this amount of thrombin, formation of fibrin fibers, size of a clot, and amount of thrombin. Well, so that's an example that in the way that your body heals, then the size of the clot is actually going to increase the amount of this thing called thrombin, which actually causes your body to generate more of these so-called fibrin fibers, which actually then increases the size of the clot. And so we get inside your body's response to having an intrusion, there is a positive feedback loop that ends up helping to seal the clot. So that's a good thing, but you know that you don't constantly keep forming scabs, or else you just have scabs that would be growing forever. So, so when we look at this, we also see that there's this other feedback loop going on here, or up here, you can see this kind of feedback loop here, in which case the size of the wound opening, well, it turns out that that increases the formation of these fibers, which we know increase the size of the clot. But as you get a scab, basically, the wound opening starts closing off. And so that ends up being a negative loop here. And so up here, you end up having a negative feedback loop. And so it maybe is not surprising that you get an S-shaped growth archetype out of the system that responds to, this is your sort of innate immune system. You know, as you get an intrusion, you don't realize it's there, but the instant you get the intrusion, you then, your body kicks into high gear, and it starts forming a temporary barrier. And once that temporary barrier is big enough, then it stops forming that barrier. And so it turns the process off, and then it disappears. And so that's kind of an example where if I were to give you, and there's other sort of loops that are happening here, I could give you something like this, ask you to label the links and try to label the loops. And then if there are archetypes, and they would be pretty obvious archetypes, then I might ask you to say, do you notice any particular type of archetypes? Or I might ask you to interpret that, like, you know, something about, you know, what does the existence of the S-shaped growth archetype imply about the system? And you'd have to know that that implies there's kind of like a rapid increase in this case, a clot, followed by a decrease in activity over time. So, and I've got, I think, on the next slide, all of these labeled. So if you'd like to try this one at home, then you've got all of those here. And I think if I look through that, there's definitely 2 loops here, and I don't think there's any other loops here. All right, so, so any questions about that example? So again, I would give you something that's less requiring a little bit of background in physiology to understand, but this is an example where I could give you something involving a system we haven't seen before and ask you to label the links and label the loops. This I think is talking about, when we're talking about spasms here, the constriction in the blood, which is going to cause sort of a constriction, I think, in the size of the opening there. I think that's what they're modeling here. All right, so limits to success, Kim and Lehman. All right, so other things, I've mentioned this kind of before. Let me bring the chat up, make sure I don't miss anything. So simulation outputs. So here's an example of, these are all simulation outputs generated from the same system. And you know, on an exam, you could read these a little bit better, but this is dt is equal to 0.1, 0.05, 01, 005, 001, 0005. The particular values don't matter so much, but the fact is that they're getting smaller as we go down through here. Now, something that's important to note, and I think I'll note this on the next slide, all of these axes go up to 500. So there's no scaling differences in the way these are plotted here, which helps to see the kind of changes over time here. And so I can see that these 3, this one, they all are simulated for 6 time units, say 6 seconds. This one gets up to 300, this goes up to 350, this goes up to almost 400, this hits 400, this pretty much hits 400, and this looks like, these 2 here look identical. So if I were to show you these, I might ask, you know, which plot kind of shows you the ideal time step? And so this could be labeled, you know, A, B, C, D, E, F. And so if I were to label those here, so I'll call this A, B, C, D, E, F. What do you think would be the best time step to use? Go ahead. Yeah, I would say E is probably a good answer. I would say that I would have less ambiguity on an exam here. I kind of wanted to sort of generate a little discussion. And I'd say E would be a very relevant answer because as you said, E and F look identical, but E has got a bigger time step. And why is it important to have as big of a time step as possible? Easier to compute or less time to compute. So less steps of the spreadsheet. You know, as you guys have now seen, as you make DT smaller, you got to have more and more rows of that spreadsheet. Yeah. Yeah, and so this again, and on yeah, so there's going to be so there will be less ambiguity on the exam, but again, for here, for discussion purposes, there could be some argument about D versus E. If you look E versus F, there is like zero difference. If you look really closely, D versus E, D does under approximate E a little bit. So we're still approaching convergence, but then you have to say, well, what's the cost? And so for my particular application, maybe the little bit drop in precision here isn't that important. Like if I'm looking for an effect size of 100 units, whatever these Y units are, then in reality, these don't differ by more than 100 units, in which case maybe this is even better because like you said, it's 5 times the step size. So I get a huge cost savings here. So in reality, it's a much more complicated sort of situation, but I don't think would get fired by anybody if you chose C, D, or E. But you personally, if you were asked for results, the difference between getting your results on Friday and getting your results on Monday might be the difference between choosing among these three. And so being able to know that it'd be really nice to use F, but D gets me home earlier, that's kind of the importance of those. So as long as you can have those conversations and be able to defend your solutions, that's great. If you're looking at this and saying, I have no idea why it shouldn't be A, then that's something that we should talk about because, and that's not meant to pick on anybody. Like, if you will look at this, what should you take from this? You should take from this that A is definitely not it. F is probably not it because F and E are identical. If you look at this and that makes total sense to you, you're in really good shape for the midterm. If you're still having trouble understanding why A is bad, then we should talk about that. So are there any questions about this? Do people sort of see why A is a bad choice for time step? Yes, I mean, so even like doing these sort of pilot studies to figure out whether you're in the ballpark of the right time step is going to require you to run this on a case-by-case basis for each one. And then deciding what is a good convergence bound, that also is going to vary on a case-by-case basis. And so, the quantitative choice of time step is something that will require you to sort of look to the problem. But qualitatively, this pattern will exist where I would say, regardless of your application, you're probably going to be sitting kind of along this diagonal. I would say there is something equivalent to, in statistics, we would talk about a minimum detectable effect size, and that would determine your statistical power. And it's the same idea here, where if it's really important for you to differentiate between 4 units, then you better make sure you converge within 4 units. If you've got enough room for 100 units, you got a lot more freedom to do a cheaper experiment. Yeah. Sounds great. Oilers, yep. Or yeah, yeah, no, that's fine. No, that wasn't meant to be a correction. It just, yeah, the Euler's method. Yep. No, no, I mean, I would say if you understand that spreadsheet, like if I could show you that spreadsheet and ask you questions about it, you understand Euler's method. That's Euler's method. So like if I ask, if in a more advanced class, I might ask you the difference between Euler's method and the Runge-Kutta integration method. And that will be much more complicated. So I see it's 5:45 now. I just want to see if there's any other important things. Oh, yes. Yeah, so the only other thing I want to point out to you, if I do give you these plots, make sure their scaling is the same, because that's going to definitely change how these work. If I can get that to go away. Okay, there. Other things, I could show you a graph like these, where I've got inflows and outflows. I would recommend looking back at this slide. I think it's a really cute example. We don't have time to go over it here, but try to understand why this time 14, where inflow is equal to outflow, represents when, in this case, these bees have the maximum number of bees in the hive. I think it's a cute example to sort of test that. Try to guess formulas, simple formulas based on units and information from the stock and flow diagram about what's going into what. Those are good things. And then if I give you formulas like this, see if you can turn them into stock and flow diagrams. Last thing, so again, more formulas, coupled stock and flow diagrams. And then, like I said, this is another example I recommend you take a look at. If I give you a set of equations like this, can you turn them into the stock and flow diagrams? Can you label their links? Can you find their loops? Can you make sure that you catch these the way that outflows here? So like notice a negative direction, this can be implemented as an outflow or an inflow with a negative formula. But typically, if you see these minuses, you typically implement them as outflows. So if you have questions about these things, then feel free to email me over the weekend or on Friday, and I'd be happy to help. But I think that's, and then that's how you then would turn this into a stock and flow diagram. Turn the flow into a variable, leave the stocks as they are, connect them up. And that, I think, is all I've got. So I won't keep you any longer. I'm not going to have an attendance question today. You don't have to come Tuesday, but you're welcome to. And likewise Thursday. Yep. Yep. Let me just stop the recording and then so for those online, I'm just going to go ahead and stop the recording, but I will stick around if you have any questions yourself. Just give me 1 second.